somewhere above the clouds of a planet you have never touched, a storm has been turning for longer than any human being has been alive, longer than any nation currently existing on Earth has held its borders, longer than most languages spoken today have existed in their current form. It is still turning right now, as you listen to this. Tonight, we are going to look closely at Jupiter's Great Red Spot, a storm so large that 3 Earths could be placed inside it side by side, so violent that its outer winds move faster than the strongest hurricanes ever recorded on our planet, and so old that nobody alive today has ever known a version of Jupiter without it. But here is the part that tends to surprise people the first time they truly understand it. A hurricane on Earth is frightening because of what it does to us. The coastlines it reshapes, the cities it empties, the lives it disrupts. The Great Red Spot has never touched a single human life directly. No one has ever stood beneath it. No ship has ever been damaged by its winds. And yet, once you understand what is actually happening inside it, you may find yourself concluding that it is a far more unsettling object than any storm Earth has ever produced. Because Jupiter's storm reveals something that our storms cannot. It shows us what weather looks like when there is nothing to stop it. No coastline to weaken it. No mountain range to break its winds. No ocean to rob it of energy. No solid ground to drag against its base and slow its spin. It shows us, in other words, what a storm becomes when nature is allowed to run the experiment for centuries without interference. By the end of this journey, you will understand why some planetary scientists consider the Great Red Spot one of the most important weather systems in the entire solar system. Not because of its size alone, but because of what its survival tells us about the hidden architecture of gas giants, about the limits of atmospheric physics, and about how differently the universe behaves once you remove the very things that keep storms on Earth in check. To understand why this storm is different from anything we experience at home, we first need to leave home behind entirely and travel out past the asteroid belt into the region of the solar system where the rules of weather begin to change. Jupiter sits roughly 5 times farther from the Sun than Earth does. Sunlight that reaches Jupiter's clouds has already faded to a fraction of the brightness we take for granted. And yet, Jupiter is, in many ways, the most dynamic weather-producing world in the solar system. That alone raises a quiet contradiction worth sitting with for a moment. Weather on Earth is driven overwhelmingly by heat from the sun. Warm air rises, cool air sinks, moisture evaporates and falls again, and the engine driving nearly everything we call weather begins with sunlight striking the ground. Jupiter receives only a small fraction of that sunlight. So where does a storm system 3 times the width of our entire planet get the energy to keep spinning for centuries? The answer turns out to be one of the strangest facts about Jupiter, and it is worth holding on to, because we will return to it. Jupiter generates more heat from within itself than it receives from the Sun. The planet is, in a very real sense, still glowing faintly from its own formation, radiating away energy left over from a birth that happened 4.5 billion years ago. This detail becomes important later, because it means the storms of Jupiter are not simply reactions to the Sun. They are partly powered by the planet's own internal furnace, a furnace that has never gone out. Jupiter itself is enormous almost beyond intuition. If you gathered every other planet in the solar system together, Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, all of them combined, and place them on one side of a scale, Jupiter alone would still outweigh them by more than 2.5 times. It is not simply the largest planet. It is more massive than everything else orbiting the Sun combined, aside from the Sun itself. And Jupiter has no solid surface at all. This is one of the hardest things for people to accept intuitively, because we are used to imagining planets as places you could, in principle, stand on. Jupiter is not that kind of world. If you tried to descend toward its center, there is no ground waiting for you. There is only atmosphere, thickening slowly into a strange, dense ocean of hydrogen, which eventually, under crushing pressure, begins behaving less like a gas and more like a liquid metal. There is no coastline. There is no continent. There is no mountain range to slow the wind down. There is simply layer after layer of moving atmosphere, all the way down. This single fact is the beginning of everything strange about the Great Red Spot. Because on Earth, storms are not simply weather phenomena. They are also victims. Victims of geography. A hurricane crossing warm ocean water can intensify rapidly, but the moment it reaches land, it begins to die. Friction from the ground disrupts its structure. Its supply of ocean moisture is cut off. Mountains shred its organized winds into chaos. Within days, sometimes hours, even the most powerful hurricane on Earth is reduced to rain and memory. Jupiter's storm has never made landfall because there is no land to make. Let that sit with you for a moment, because it is the first real key to understanding why this storm behaves so differently from anything in our experience. Every storm you have ever heard about on Earth, every hurricane, every typhoon, every cyclone, existed inside a system that was always working to kill it. The Great Red Spot exists inside a system with no mechanism built in to stop it. Astronomers have been watching this storm in one form or another since the 1600s. In 1665, the astronomer Giovanni Cassini observed a persistent dark oval on Jupiter through his telescope, and he tracked it for years. Whether that exact feature is the same storm we observe today is something scientists still debate, because there is a gap in written observations during the early 1700s, and it is possible the original spot faded and a new one eventually formed in a similar latitude. But continuous, unambiguous documentation of the Great Red Spot in its modern form stretches back to at least 1830. And many researchers believe the observational trail reaches back further still. That means, at minimum, this storm has been raging continuously for close to 2 centuries. Some estimates, factoring in the earlier Cassini observations, push its possible age past 350 years. Try to picture what that actually represents. If the storm has existed since the 1830s, it was already turning before the American Civil War. It was already turning before the invention of the telephone, before the first photograph of a human face, before electricity reached ordinary homes. Generations of astronomers have been born, trained their entire careers pointing telescopes at Jupiter, and died, all while this single storm continued spinning above the clouds, indifferent to any of it. No hurricane on Earth has ever lasted longer than a few weeks. The very idea of a storm outliving multiple human lifetimes should feel almost impossible. And yet there it is, a visible feature on a planet 500 million miles away, patiently waiting for the next telescope to be pointed its way. This is where the first real question begins to form, the one that will guide us through everything that follows tonight. If nothing on Earth prepares us to understand a storm like this, If every mechanism we associate with the death of a storm simply does not apply on Jupiter, then what does keep a storm alive? What are the actual physical rules governing something that has no coastline to die against, no landmass to disrupt it, and only a distant, weakened sun for outside energy? To answer that, we need to look at what the Great Red Spot actually is, mechanically speaking, and how it holds itself together, despite everything working, in theory, to tear it apart. The Great Red Spot is what atmospheric scientists call an anticyclone, a rotating storm system that spins in the opposite direction to the low-pressure cyclones we associate with hurricanes on Earth. On Earth, a hurricane is a low-pressure system. Air rushes inward and upward, drawing energy from warm ocean water as it rises, then spirals outward at high altitude. The Great Red Spot works in reverse. It is a high-pressure system, meaning that within it, air is sinking rather than rising, and the storm rotates counterclockwise in Jupiter's southern hemisphere due to the Coriolis effect operating in reverse compared to what we experience at home. This distinction matters enormously because it changes the entire physical character of the storm. Anticyclones on Earth tend to be associated with calm, clear, stable weather. Think of the high-pressure systems that bring bright, sunny days. They are usually gentle. They are usually the absence of drama, not the source of it. Jupiter's anticyclone is anything but gentle. Wind speeds along the storm's outer edge have been measured at roughly 430 kilometers per hour, close to 270 miles per hour. To put that number into perspective, the strongest hurricane wind speeds ever recorded on Earth top out at around 315 kilometers per hour. And storms of that intensity are vanishingly rare, appearing perhaps once in a generation. Jupiter's storm doesn't reach these speeds briefly during a peak intensification phase. It simply operates at this level more or less continuously, because there is nothing present in the system to slow it down, and the storm is not small. Current measurements place the Great Red Spot at roughly 16,000 kilometers across, at its widest point. As of recent decades, it has actually been shrinking, a detail we will return to later, because it was once significantly larger, wide enough that three have been placed side by side within its boundary. Even in its diminished modern state, it remains wide enough to comfortably swallow the entire planet Earth, with room left over. Now picture that scale next to the storms you have personal experience with. A large hurricane on Earth might stretch several hundred kilometers across. The Great Red Spot is not several hundred kilometers across. It is measured in tens of thousands. You are not looking at a bigger version of a hurricane. You are looking at a phenomenon operating on an entirely different order of magnitude. The way a mountain range operates on a different order of magnitude than a single hill. For a long time, planetary scientists assumed the Great Red Spot, however large, was probably a relatively shallow feature. A colorful surface disturbance sitting atop deeper, calmer layers of Jupiter's atmosphere. The way a wave sits atop the ocean without disturbing the water far below. This assumption turned out to be wrong, and the moment scientists discovered how wrong it was, became one of the more genuinely startling revelations in the modern exploration of Jupiter. We'll get to exactly what was found in a moment. But first, it's worth pausing here, in these early minutes of the journey, to acknowledge something. If you find yourself enjoying this slow, careful unfolding of one of the strangest weather systems in the solar system. You're welcome to leave a like on this video and to subscribe if you'd like to keep exploring stories like this one. It helps this quiet corner of the internet keep going. And there are many more evenings like this one ahead, spent looking closely at the strange and beautiful mechanics of worlds far from our own. Now, let's continue further into the storm, because the deeper questions are only just beginning to surface. For most of the 20th century, our understanding of the Great Red Spot came primarily from what telescopes and passing spacecraft could observe from above. The colors, the shape, the rotation, the wind speeds at the cloud tops. What lay beneath those clouds remained largely a mystery, simply because nothing had ever been built that could look downward into Jupiter's atmosphere and measure what was happening at depth. That changed with the arrival of a spacecraft called Juno, which entered orbit around Jupiter in 2016 and was equipped with instruments specifically designed to peer beneath the visible cloud layer. Juno carried a microwave radiometer capable of sensing thermal emissions from deep within Jupiter's atmosphere, essentially allowing scientists to build a kind of vertical map of the storm, layer by layer, rather than relying solely on the surface view available to previous observers. What Juno found reshaped the scientific understanding of the storm almost immediately. The Great Red Spot was not a shallow surface feature at all. Its roots extended downward at least 300 kilometers beneath the visible cloud tops. And some analyses suggest the true depth may reach even further, potentially several hundred kilometers into the planet's atmosphere. To put that into perspective, Earth's own atmosphere, from the ground up to the point where space effectively begins, is only around 100 kilometers thick in total. The Great Red Spot's roots alone extend deeper than the amphitrite of Earth's atmosphere. This finding quietly overturned decades of assumption. Scientists had long imagined the storm as something like a great colored disk floating on Jupiter's cloud deck. Dramatic to look at, but ultimately thin. Juno revealed instead that the Great Red Spot behaves more like an iceberg, with a small visible portion above and a vast unseen structure extending downward, deep into the planet's interior atmosphere. Anchored in place by forces we are still working to fully understand. This depth appears to be part of the answer to why the storm has survived for so long. A shallow storm is vulnerable. It can be disrupted easily by disturbances above or below it, the way a thin layer of oil on water can be broken apart by the smallest ripple. A storm with deep roots, extending hundreds of kilometers into a planet's atmosphere, is a different kind of structure entirely. It is not merely floating on the surface of Jupiter's weather, it is embedded within it, drawing stability from layers of atmosphere that are themselves shielded from the disturbances affecting the visible cloud tops. And this raises a genuinely unsettling thought, one worth sitting with for a moment. If the visible red oval we can photograph from Earth is only the surface expression of something far larger and deeper, then in a very real sense, we have never actually seen the true size of the Great Red Spot. We have only ever seen its uppermost signature, the part of the storm that happens to catch sunlight and reflect it back toward our telescopes. The true structure, the actual bulk of what is spinning down there, remains hidden beneath clouds no camera has ever penetrated. This is a theme we will return to throughout this exploration. The idea that Jupiter consistently reveals only a fraction of itself, and that everything we find fascinating about the Great Red Spot from a distance is very likely a pale hint of something considerably stranger occurring beneath the visible surface. Now, let's address a question that almost everyone eventually asks the first time they see an image of Jupiter. Why is the Great Red Spot red at all? This turns out to be one of the more genuinely unresolved mysteries in planetary science. And it is worth being honest about that up front, rather than pretending there is a tidy, settled answer. Jupiter's atmosphere is composed overwhelmingly of hydrogen and helium, the same two elements that dominate the composition of the Sun itself. Neither of these gases is red. Neither of these gases, on its own, would produce any color at all. So the color we see must be coming from something else, some additional ingredient mixed into the storm that interacts with sunlight in a very particular way. For decades, the leading hypothesis centered on a compound called ammonium hydrosulfide, thought to form clouds within Jupiter's upper atmosphere and to somehow become chemically altered by exposure to ultraviolet sunlight, producing reddish compounds as a byproduct. This remains a plausible partial explanation, but more recent laboratory experiments have introduced competing possibilities. Some researchers have proposed that the reddish material may instead involve more complex compounds formed when ammonia and acetylene, both present in Jupiter's atmosphere, are broken apart by sunlight at high altitude and recombine into new molecules capable of absorbing blue light and reflecting red. The same basic principle behind why the sky above your head appears blue, except operating in reverse on an alien mixture of chemicals none of us have ever directly sampled. There is something worth noticing in this uncertainty. We can measure the storm's wind speed with remarkable precision. We can measure its depth, its temperature, its rotation. And yet, if you were to ask a planetary scientist today to tell you with full confidence exactly which molecule is responsible for the single most visually recognizable feature on the largest planet in the solar system, the honest answer remains: we are still working it out. This is worth remembering as we go, because it says something about the limits of even our best current understanding. We are not simply cataloging a fully solved phenomenon tonight. We are exploring the edge of what is currently known, and in some places, quietly stepping past that edge into what remains genuinely uncertain. What we do know is that the color is not constant. Historical records and photographs from different decades show that the Great Red Spot has, at various points, appeared as a pale salmon color, a much deeper brick red, and at times so faded that observers questioned whether the red in its name still applied at all. Something in the chemistry driving its color appears to shift over time, likely tied to changes in the storm's internal temperature, the altitude of its highest cloud layers, or the amount of material being lifted upward from deeper in the atmosphere by the storm's churning motion. This detail matters more than it might first appear, because it hints at something important. The Great Red Spot is not a static object. It is not a fixed, unchanging feature, simply sitting on Jupiter's surface like a scar. It is a living, breathing weather system, continuously exchanging material with the layers of atmosphere above and below it, its color rising and falling like a kind of slow, centuries-long breathing pattern that we are only now beginning to notice across generations of observation. Let's return, for a moment, to the question of scale, because there is a deeper layer to it than simple size comparison. Earlier, we described the storm as wide enough to fit the entire planet Earth within its boundary. But scale in this context is not just about width. It is also about energy. A hurricane on Earth, however powerful, is ultimately a relatively modest energy system compared to the total climate machinery of our planet. It draws its strength primarily from warm surface water across a few hundred kilometers of ocean, and even the strongest hurricanes represent a tiny fraction of the total energy budget flowing through Earth's atmosphere at any given moment. The Great Red Spot operates on a completely different scale of the planet's total energy system. Jupiter's atmosphere is arranged into alternating bands of jet streams, light-colored zones and darker belts that circle the entire planet at tremendous speed, driven by a combination of the planet's rapid rotation, its internal heat. Jupiter completes a full rotation in under 10 hours, despite being more than 11 times wider than Earth. This means that a single point on Jupiter's equator is moving through space at a rotational speed far greater than any point on Earth ever experiences. That rotational speed is the engine behind the ferocious, banded jet streams that define Jupiter's entire visible surface, and the Great Red Spot sits wedged between two of these opposing jet streams, essentially caught between two rivers of atmosphere flowing in opposite directions at speeds that would be almost unimaginable in Earth's atmosphere. This positioning is not incidental. Many researchers believe it may be one of the actual keys to the storm's extraordinary longevity. The Great Red Spot sits in a kind of atmospheric channel, bounded on its northern and southern edges by jet streams moving in opposite directions relative to each other. In effect, the storm is trapped between two conveyor belts moving opposite ways, and this arrangement may act like a kind of natural containment system, continuously feeding energy into the storm's rotation from both sides, while simultaneously preventing it from drifting apart or dissolving into the surrounding atmosphere. Picture two rivers running parallel to each other, flowing in opposite directions, with a whirlpool trapped in the narrow gap between them. As long as both rivers keep flowing, the whirlpool has a continuous supply of rotational energy feeding into it from both sides. It does not need to generate all of its own energy internally, because the surrounding jet streams are, in effect, doing some of the work for it, continuously. If this explanation holds up, and current evidence increasingly supports it, it means the Great Red Spot's survival is not simply a matter of the storm being unusually resilient in isolation. It survives because it is positioned, almost perfectly, within a structural feature of Jupiter's atmosphere that continuously reinforces it. It is less like a candle burning on its own fuel, slowly running out, and more like a flame positioned directly above a vent of continuously rising gas, sustained for as long as that vent continues to exist. This raises an important question, one that will carry us into the next major part of this exploration. If the storm depends on the surrounding jet streams for its long-term survival, then is this storm truly permanent? Or is it, in a much deeper sense, entirely dependent on the stability of a much larger, planet-wide weather system that we are only beginning to understand? And if that larger system were ever to shift, even slightly, what would happen to the storm sitting trapped between its two opposing currents? We are going to come back to that question, but to answer it properly, we first need to understand something about the storm that surprised almost everyone who has studied it closely over the past several decades. It is shrinking, and the story of exactly how much it has shrunk, how quickly, and what that might ultimately mean for its future turns out to be one of the more quietly unsettling chapters in the entire story of Jupiter's most famous storm. When the Great Red Spot was first measured with reasonable precision in the late 1800s, astronomers recorded its width at somewhere around 40,000 kilometers, roughly 2.5 times the diameter of Earth, stretched across a single storm system. Photographs and drawings from that era show an oval so large that it dominated nearly a third of Jupiter's visible southern hemisphere when viewed through the telescopes of the day. By the time the Voyager spacecraft flew past Jupiter in 1979, the storm had already noticeably contracted, measuring closer to 23,000 kilometers across. That is still enormous by any reasonable standard, still wide enough to comfortably swallow Earth nearly twice over, but it represented a significant reduction from the measurements taken a century earlier. The shrinking did not stop there. Observations from the Hubble Space Telescope across the following decades documented a slow, steady, almost eerily consistent decline in the storm's overall size. By the early 2010s, the Great Red Spot had narrowed to roughly 16,000 kilometers across. The figure we mentioned earlier, and some measurements taken more recently, suggest the contraction may still be continuing, even as the storm has also become noticeably rounder over time, shifting from the elongated oval shape of historical photographs towards something closer to a circle. This detail, the shift from oval to circle, turns out to matter a great deal, because in atmospheric physics, shape is not a cosmetic detail. It reflects the underlying balance of forces holding a rotating system together. An elongated storm generally indicates that outside forces, such as the surrounding jet streams, are actively stretching it along one axis. A storm that becomes progressively rounder over time may indicate that it is settling into a more stable, lower energy configuration. Or, more concerning to some researchers, that it may be losing the structural tension that once kept it stretched into its historically iconic oval shape. Naturally, this has led to public speculation, sometimes overstated in headlines, that the Great Red Spot might be dying, potentially disappearing, within a matter of decades. It is worth being precise and honest here, because this is exactly the kind of claim where scientific caution matters. The truth is that scientists do not currently know, with certainty, whether the storm is approaching some kind of terminal decline, or whether it is instead settling into a new, smaller, but potentially stable long-term size. The way fire might down from a large blaze to a smaller, steadier flame that continues burning indefinitely rather than going out entirely. Some researchers have pointed to a curious detail supporting the second, more stable possibility. Even as the storm's width has decreased, its vertical extent, its depth, height above the cloud deck, and overall wind speeds has not shown a corresponding collapse. If the storm were truly dying in a straightforward sense, many scientists would expect to see its wind speeds weakening and its structure destabilizing across all dimensions simultaneously, not merely narrowing in one direction while remaining otherwise intact. There is also a historical argument for caution. Remember that our clearest, most confident measurements only stretch back roughly 150 years. It is entirely possible that the Great Red Spot has expanded and contracted many times across the centuries before anyone was carefully measuring it, and that what we are currently witnessing is not necessarily the final act of a dying storm, but simply one phase within a much longer cycle of growth and contraction that we do not yet have enough historical data to fully map. This uncertainty is, in its own way, one of the most quietly fascinating aspects of the entire story. We are watching something we cannot yet categorize. We do not know if we are witnessing the slow final centuries of the largest storm in the solar system, or simply one chapter in a much longer story, whose beginning we already missed by hundreds of years, and whose ending, if there even is one in any time frame relevant to human civilization, remains entirely unknown. And this brings us to something worth pausing on. The storm's fate is not simply a curiosity about Jupiter. It is quietly tied to a much larger question that reaches into how planetary atmospheres behave in general, one that becomes especially important once you start comparing Jupiter's storm to similar phenomena elsewhere in the solar system, because Jupiter is not the only gas giant to have hosted a storm of this kind. And what happened to one of its cousins may be the closest thing we have to a preview of what could eventually happen here. In 1989, the Voyager 2 spacecraft became the first, and so far only, spacecraft to fly close enough to Neptune to photograph its atmosphere in real detail. Among its discoveries was a dark, oval-shaped storm system in Neptune's southern hemisphere, promptly named the Great Dark Spot. It bore a striking resemblance to Jupiter's storm, a massive, rotating, high-pressure system, roughly the width of Earth itself, clearly visible against the pale blue backdrop of Neptune's atmosphere. At the time, many assumed it might be a permanent feature of Neptune's climate, much like the Great Red Spot appeared to be for Jupiter. 5 years later, in 1994, the Hubble Space Telescope turned its attention back toward Neptune to check on the storm's progress. It was gone. Not shrunk, not faded, gone entirely, vanished from the location where it had been photographed just years earlier, with no clear trace remaining. In its place, Hubble instead detected a new dark spot forming in Neptune's northern hemisphere, a storm that had not existed at all during the earlier Voyager flyby. This was, to put it plainly, a genuine shock to planetary scientists at the time. It demonstrated, with clear photographic evidence, that these giant storm systems on gas giants are not necessarily permanent fixtures at all. Some can apparently form, persist for a handful of years, and then completely dissolve back into the surrounding atmosphere, only for entirely new storms to emerge elsewhere on the planet within a similarly short span of time. This single discovery reframes the entire question of Jupiter's storm in an important way. It tells us that the default behavior of large atmospheric vortices on gas giants may not be permanence at all. It may be transience. Storms may form, persist for a while, sometimes centuries, sometimes only a handful of years, and then vanish, their material reabsorbed into the broader atmospheric currents from which they emerged. If that is the underlying rule governing these systems, then the Great Red Spot is not simply a storm. It is an extraordinary outlier. It is the survivor. Whatever combination of size, depth, positioning between opposing jet streams, and internal energy has kept it intact, it has managed something that Neptune's storm, similar in so many respects, conspicuously failed to do. And this raises the question we set aside earlier, the one about the storm's dependency on the surrounding jet streams. If Neptune's Great Dark Spot could simply disappear within a matter of years, despite looking, from a distance, remarkably similar to Jupiter's storm, then what precisely is different about Jupiter's atmosphere that has allowed its storm to persist for centuries, rather than years? Is it purely a matter of scale? Jupiter being so much larger and more energetic than Neptune, that its storms are simply built to last longer by default? Or is there something more specific about the exact latitude, the exact jet stream configuration, the exact depth of atmosphere the Great Red Spot happens to be anchored within, that has allowed it to succeed where its Neptunian cousin failed? This is one of the genuine open frontiers of planetary atmospheric science, and it connects to something larger than Jupiter alone. Because if we can understand precisely why one storm on one gas giant survives for centuries, while an almost identical storm on a neighboring gas giant vanishes within years, we begin to understand something fundamental about how atmospheres in general organize themselves. Knowledge that becomes increasingly relevant as astronomers turn their telescopes toward the thousands of gas giant exoplanets now known to exist around other stars, many of them almost certainly hosting storm systems of their own. Storms no human telescope has yet been powerful enough to directly observe. We are going to return to that thought later. The idea that the Great Red Spot may, in a strange way, function as a kind of natural laboratory, teaching us lessons that apply far beyond Jupiter itself, potentially to worlds orbiting stars we cannot see without a telescope. But before we can properly explore that connection, there is a more immediate mystery we have not yet addressed directly, one that returns us to the question we raised near the very beginning of this journey. We describe Jupiter's storm as more terrifying, in a very real sense, than any storm on Earth. We have now established its size, its wind speeds, its depth, its uncertain chemistry, and its unusual position between opposing jet streams. But terror, in the way we are using the word here, is not really about size or wind speed alone. Genuine unease comes from something deeper, from confronting a process that operates entirely outside the rules we instinctively expect nature to follow. And there is one particular property of the Great Red Spot that does exactly this, a property that becomes clear only once you start asking what would actually happen if a storm like this ever encountered something solid. Because on Earth, every storm we experience eventually meets resistance. It meets land, it meets mountains, it meets friction against the ground, which slowly bleeds energy out of even the most powerful hurricane until it collapses into ordinary rain. This resistance is not a minor detail. It is, in effect, one of the fundamental safety mechanisms built into Earth's climate system, an upper limit on how long any single storm can persist, enforced by the simple fact that our planet has a solid surface for storms to eventually collide with. Jupiter's storm has no such safety mechanism, because Jupiter itself has no solid surface anywhere to be found. There is no coastline the Great Red Spot could ever reach. There is no mountain range waiting to break its winds apart. There is no ground for it to drag against and lose momentum. In an important physical sense, the Great Red Spot is a storm without an ending, built into the very structure of the world it inhabits. A storm existing inside a planet that has quite literally no mechanism available to stop it, other than whatever internal atmospheric dynamics might eventually cause it to dissipate on its own. This is the deeper, more unsettling truth, sitting beneath everything we have discussed so far tonight. It is not simply that the Great Red Spot is bigger or faster or older than any storm on Earth. It is that the Great Red Spot exists in a universe of physical rules subtly different from our own. A universe where the checks and balances that quietly limit the life of every storm we have, personally ever feared, simply do not exist. Whatever eventually happens to this storm, whether it shrinks slowly into nothing over the coming decades, or somehow stabilizes and continues spinning for centuries more, its fate will be decided entirely by forces internal to Jupiter's atmosphere itself. Forces we are still only beginning to properly measure and understand. And that leads us toward a much larger question, one that reaches beyond the storm itself and into the deeper architecture of Jupiter as a planet. Because if the Great Red Spot is powered partly by Jupiter's internal heat, positioned between two of the planet's great jet streams, and routed hundreds of kilometers into an atmosphere with no solid floor beneath it anywhere, then understanding this storm really means understanding something much bigger. It means understanding what kind of planet could produce a weather system like this in the first place, and why gas giants across our solar system, and very likely across countless others we have not yet directly observed, seem to build their storms according to an entirely different rule book than the one written into the atmosphere of our own quiet, solid, storm-limited world. That is where we are going to travel next. Deeper into Jupiter itself, into the layers beneath the clouds, into the furnace of heat left over from the planet's own formation, and into the question of what it would actually mean for Jupiter and for us if a storm like this one were ever to finally come to an end. To understand the furnace powering this storm from below, we have to go back to the very beginning of Jupiter's existence, roughly 4.5 billion years ago, when the solar system itself was still little more than a spinning disk of gas and dust surrounding a newly formed sun. In the outer regions of that disk, far beyond where rocky planets like Earth and Mars would eventually take shape, conditions were cold enough for ices, water, ammonia, methane, to remain frozen rather than boiling away as they would closer to the sun's heat. This allowed a solid core to grow relatively quickly, accumulating icy and rocky material until it reached a mass several times greater than Earth's. Once that core became large enough, its gravity was strong enough to begin pulling in the surrounding hydrogen and helium gas directly from the disk, a runaway process that added mass at an extraordinary rate. Jupiter grew so quickly and pulled in so much gas that it likely reached most of its current mass within just a few million years. A blink of an eye in astronomical terms, and this rapid, violent accumulation of material left something behind. Heat, an enormous amount of gravitational energy, was converted into thermal energy as gas fell inward and compressed under Jupiter's own increasing gravity. In a very real sense, Jupiter was born already hot, glowing internally from the sheer violence of its own formation. That primordial heat has never fully gone away. Jupiter is so massive that its interior continues, even today, to slowly compress under its own gravity, a process called Kelvin-Helmholtz contraction, in which the planet very gradually shrinks by perhaps a few centimeters per year, and converts the resulting gravitational energy into heat that radiates outward toward the cloud tops. This means Jupiter currently emits roughly 1.5 to 2 times more energy into space than it receives from the sun. The planet, in effect, still glows faintly with the memory of its own birth 4.5 billion years later. This detail matters enormously for understanding the Great Red Spot, because it means Jupiter's weather is not simply a passive response to sunlight, the way weather on Earth largely is. Jupiter's atmosphere is being driven from below as well as from above, heated internally by a planet still radiating away energy from its own formation, and heated externally, faintly, by a distant sun's two separate heat sources. Working simultaneously on the same restless atmosphere is part of why Jupiter's weather is so much more violent and so much more enduring than anything Earth produces. Using sunlight alone to really appreciate what lies beneath the storm, it helps to travel downward through Jupiter's atmosphere layer by layer, the way Juno's instruments have allowed scientists to do. At the very top, where the Great Red Spot's reddish cloud deck catches sunlight and becomes visible to our telescopes, temperatures are bitterly cold, plunging to roughly -145 degrees Celsius. This is the layer we see in every photograph of Jupiter ever taken. A thin, deceptively calm-looking ceiling sitting atop a much stranger world underneath. Descend further, and the atmosphere thickens and warms, passing through layers of ammonia ice clouds, then ammonium hydrosulfide clouds, then deeper still, water clouds, not unlike the clouds that produce rain here on Earth, except occurring at pressures many times greater than anything in our atmosphere. Descend further still, and the hydrogen and helium making up the bulk of Jupiter's atmosphere begin to behave strangely. The pressure becomes so extreme that hydrogen gas is compressed into a hot, dense fluid, and eventually, at pressures millions of times greater than what we experience at Earth's surface, the hydrogen is squeezed so tightly that its electrons are stripped away from their atoms entirely, and it begins to conduct electricity like a metal. This exotic state of matter, known as metallic hydrogen, is believed to make up the bulk of Jupiter's deep interior, and its churning, electrically conductive motion, driven by the planet's rapid rotation, is thought to generate Jupiter's magnetic field, by far the strongest of any planet in the solar system, roughly 20,000 times stronger than Earth's. This is worth pausing on, because it reframes everything we have discussed about the Great Red Spot so far. The storm we can photograph through a telescope from 100 million kilometers away is only the thinnest, coldest, outermost skin of a planet whose interior is compressing hydrogen into an electrically conductive metal, generating a magnetic field powerful enough to be detected from Earth and radiating heat left over from a violent formation event 4.5 billion years in the past. The storm's roots, extending 300 kilometers or more beneath the visible clouds, are still nowhere close to reaching this deep, alien interior. And yet even at that comparatively shallow depth, the storm is already interacting with forces and pressures far beyond anything found in Earth's atmosphere. This layered structure helps explain something we touched on earlier: why the storm's energy supply appears almost inexhaustible on any timescale relevant to human history. It is not drawing its power from a single, finite source, the way a hurricane draws briefly from warm ocean water before that fuel runs out. It is embedded within a planet-wide system that is simultaneously fed by leftover formation heat rising from below and shaped by opposing jet streams racing along its northern and southern flanks. Both of these energy sources are, for all practical human purposes, effectively permanent. The internal heat will continue radiating outward for billions of years to come. The jet streams, driven by Jupiter's rapid rotation, will continue racing around the planet for as long as Jupiter itself keeps spinning. Which brings us back, with new context, to the question of the storm's shrinking size. If both of its major energy sources are, for all practical purposes, permanent and unchanging, then why would the storm be shrinking at all? What has changed? If the underlying engine driving it appears as stable now as it has been for centuries, this is one of the genuine puzzles that current research is still working through. And there are a few competing explanations worth understanding, because each one tells us something different about how fragile or how resilient this storm actually is. One leading hypothesis involves smaller storms being absorbed into the Great Red Spot over time. Jupiter's atmosphere regularly produces smaller vortices and storm systems, some lasting only weeks or months. Historical observations have documented several occasions when small storms drifted close to the Great Red Spot and were, in effect, swallowed by it, their material and momentum absorbed into the larger storm's rotation. For much of its observed history, this process may have actually helped sustain the Great Red Spot, feeding it fresh energy and material much the way a large fire can be kept burning, by continually adding smaller pieces of fuel. Some researchers now suspect that in recent decades, this feeding process may have become less frequent, or that the storm has begun losing material outward, through smaller filaments and eddies peeling away from its edges, faster than it is gaining new material from these absorption events, resulting in a slow, gradual net loss of overall size. Another hypothesis focuses on the changing shape of the jet streams bordering the storm. If the boundaries between Jupiter's atmospheric bands have shifted even slightly over the past century, moving closer together, for instance, this could effectively be squeezing the storm into an increasingly narrow channel, forcing it to shrink, not because it is dying from within, but because the physical space available for it to occupy has itself become smaller. A third possibility, and perhaps the most quietly striking one, suggests that what we are calling shrinking may not represent a loss of the storm's true underlying energy at all, but rather a redistribution of that energy into a smaller, more compact, and more intensely concentrated form. Similar to how a figure skater spins faster by pulling their arms inward, conserving their overall rotational energy, while reducing their outward size. If this explanation holds, the modern Great Red Spot, though visibly smaller than its 19th century predecessor, might actually be spinning with comparable or even greater intensity per unit of area, simply compressed into tighter, more concentrated form. Some observational evidence supports this possibility. Wind speeds at the storm's edge have shown signs of increasing in recent decades, even as its overall width has decreased. A pattern that would make sense if the storm were conserving its rotational energy while shrinking in physical size, rather than simply losing energy outright. None of these explanations has yet been proven conclusively, and it may well turn out that all three are happening simultaneously, in some shifting combination, contributing to the same overall pattern of contraction. This uncertainty is not a weakness in our understanding. It is an honest reflection of how genuinely difficult it is to study a storm that sits nearly 600 million kilometers away, using instruments capable of resolving its cloud tops, but not, so far, its true internal structure with complete clarity. What is clear, regardless of which explanation eventually proves correct, is that the Great Red Spot is not a static museum piece frozen in time. It is a living, evolving system, continuously exchanging energy and material with the planet around it. Its size and intensity shifting across decades in ways that we are only now, with modern instruments, beginning to properly track and record for the first time in human history. This brings us to a thought that connects everything discussed so far into a single, larger perspective. One that reaches beyond Jupiter and beyond even our own solar system entirely. For most of human history, storms were something we could only study from directly underneath them. Standing on the surface of our own single planet, watching weather systems form, intensify, and dissipate within days or weeks, always constrained by the coastlines, mountains, and solid ground that define life on a rocky world. The idea that a storm could survive for centuries, unconstrained by any solid surface, drawing power simultaneously from a planet's ancient internal heat and its high-speed atmospheric currents, would have sounded like pure fantasy to any meteorologist working even 150 years ago. And yet here it is, not a hypothetical, not a thought experiment, but an actual, observable, currently ongoing weather system, sitting in our own solar system, close enough for our own spacecraft to have flown directly through parts of its outer atmosphere and measured its properties directly. The Great Red Spot is, in this sense, a kind of natural laboratory unlike anything available to us on Earth. A real, physical demonstration of what weather becomes once you remove the very things that limit and eventually kill every storm we have personal experience with. And this laboratory is becoming increasingly relevant to a much larger question currently occupying astronomers around the world: the search for and study of planets orbiting other stars entirely. In the past 3 decades, astronomers have confirmed the existence of thousands of exoplanets, a significant fraction of which appear to be gas giants similar in basic composition to Jupiter. Enormous worlds of hydrogen and helium, orbiting stars sometimes remarkably similar to our own Sun, sometimes wildly different. None of these distant worlds can currently be photographed in anywhere near the detail we have achieved for Jupiter. Their atmospheres remain, for now, largely invisible to us, reduced to faint shifts in starlight and subtle spectroscopic signatures rather than detailed cloud-top imagery. But the physics governing those distant atmospheres is not fundamentally different from the physics governing Jupiter's atmosphere, sitting right here in our own solar system, close enough to study directly. Every lesson learned from the Great Red Spot: how storms form between opposing jet streams, how internal planetary heat can sustain atmospheric violence, independent of a host star's light, how the absence of a solid surface removes the natural limits that constrain storms on rocky worlds, becomes a piece of a larger puzzle that scientists are quietly using to build models of what weather might look like on gas giants we may never be able to photograph directly in our lifetimes. In other words, the Great Red Spot is not simply a curiosity confined to Jupiter. It may be the closest and clearest example we will ever have for a very long time of a category of storm that could be common throughout the universe, occurring silently on countless gas giants, orbiting countless distant stars, entirely unconstrained by solid ground, entirely capable of persisting for centuries or longer, entirely invisible to us except through the one nearby example we happen to have been fortunate enough to be born close enough to study. We are going to sit with that thought for a while, because it changes the entire scale of what we have been discussing tonight. This is no longer simply a story about one unusual storm on one unusual planet. It may be a story about a fundamental category of weather that exists throughout the universe. Wherever massive, sunlight-starved worlds of hydrogen and helium form around distant stars. A category of weather we would know almost nothing about, if it were not for the fact that one particularly old, particularly stubborn example happens to be spinning quietly. Right now, less than an hour's journey at the speed of light from where you are sitting tonight. It's worth taking a moment here to bring this back down to a scale we can actually feel, because numbers alone. 16,000 kilometers, 430 kilometers per hour, 300 kilometers of depth, tend to blur together after a while. The way any sufficiently large number eventually stops meaning anything concrete to the human mind. So try this instead. Picture the strongest hurricane you have ever personally experienced or watched unfold on the news. The kind that closes airports, empties coastal towns, and dominates headlines for a week. Now imagine that same storm, but stretched wide enough to swallow the country you live in, several times over in most cases. Imagine its winds not merely matching the strongest gusts ever measured on Earth, but sustaining that intensity as an ordinary, average condition, day after day, for as long as anyone has been alive to check. Imagine that storm never once weakening as it crosses a coastline, because there is no coastline anywhere on the entire planet for it to cross. And imagine that storm has already been spinning, without meaningful interruption, since a time when horse-drawn carriages were the fastest form of transportation available to human beings. That is not an exaggerated hurricane. That is an ordinary Tuesday on Jupiter. And there is something almost humbling in recognizing that this storm has never needed us in order to exist. It was turning long before Giovanni Cassini pointed a telescope at Jupiter in the 1600s. It was turning through the entire span of recorded human history that mattered to any of us personally. It will, in all likelihood, still be turning long after every person listening to this has lived out their own life and returned quietly to the Earth. We arrived late to a storm that was already ancient by the time we learned to look up and notice it, and we will most likely depart before it does. This is the strange gift hiding inside a story like this one. Not fear, exactly, though there is something to that too. Mostly, it is perspective. The reminder that the universe has been running its own experiments in physics and weather and time for far longer than any human institution, any human memory, any human civilization has existed to witness them. Jupiter's storm asks nothing of us. It does not care whether we are watching. It simply continues, indifferent and enormous, exactly as it has for centuries, exactly as it likely will for centuries more. But indifference is not the same as simplicity, and there is still a great deal about this storm that remains genuinely unresolved. We have talked about its size, its depth, its uncertain chemistry, its position between opposing jet streams, and the internal heat of a planet still glowing faintly from its own violent birth. We have not yet talked about what any of this means for the rest of Jupiter, for the other storms scattered across its bands, for the strange, smaller cousins of the Great Red Spot that occasionally form, merge, and vanish across its churning atmosphere, or for the question of what it would actually look like, mechanically and visually, if this storm ever did finally begin its true final decline. We also have not yet addressed one of the more genuinely eerie discoveries to come out of the Juno mission. A finding involving lightning, deep within Jupiter's clouds, occurring in places and under conditions that, by all conventional expectations, should not produce lightning at all. Nor have we discussed the strange, cyclical relationship between the Great Red Spot and a smaller, younger storm that astronomers have nicknamed Red Spot Junior, a storm that formed decades ago through the merger of three smaller vortices, changed color to match its larger neighbor, and now trails the Great Red Spot around Jupiter's hemisphere, like a smaller sibling forever chasing something it may never quite catch. And there is one more question hanging over everything we have discussed tonight, one that reaches past Jupiter entirely, back toward the very origins of the solar system itself. Jupiter's gravity is so overwhelming that it has shaped the orbits of comets and asteroids for billions of years, flinging some out toward the edge of the solar system and pulling others down into paths that cross dangerously close to Earth. Some researchers have even proposed that Jupiter's gravitational influence, acting over billions of years, may have played a direct role in determining which regions of the early solar system were safe enough for a planet like ours to form quietly and remain undisturbed long enough for life to take hold. If that is true, then in some strange, indirect way, the same planet producing the most violent storm in the solar system may also be part of the reason a much gentler, much smaller, much more fragile world was ever able to exist peacefully enough for you to be listening to this story at all. That thought deserves its own careful exploration. And it is exactly where we are headed next. Deeper into Jupiter's family of storms, into the lightning flashing deep within its clouds, and into the question of what this restless giant may have quietly done billions of years ago to make a place like Earth possible in the first place. We have covered a great deal of ground so far tonight, but the truth is, we have only reached the surface of what makes this storm, and the planet holding it, genuinely worth understanding. There is more to uncover, more depth to descend into, more of Jupiter's ancient, ongoing story still waiting. We have covered a great deal of ground so far tonight, but the truth is, we have only reached the surface of what makes this storm, and the planet holding it, genuinely worth understanding. There is more to uncover, more depth to descend into, more of Jupiter's ancient, ongoing story still waiting. Let's begin with something that, on the surface, should not exist at all: lightning. Before we look at that discovery directly, it helps to understand how our view of this storm has actually evolved across the age of spacecraft exploration, because each mission that has visited Jupiter added its own layer to the picture. And the story of how we came to understand the Great Red Spot is, in its own way, a story about the accelerating pace of human curiosity. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s, were the first human-made objects to fly past Jupiter at close range, sending back the first close-up images of the storm ever captured by a machine rather than a telescope. The images were grainy and limited by the technology of the era, but for the first time, human beings could see the Great Red Spot not as a smudge of color glimpsed through a telescope lens from 100 million kilometers away, but as a genuine, three-dimensional weather feature with visible texture and structure in its swirling clouds. Then came the Voyager missions in 1979, and everything changed again. Voyager 1 and Voyager 2 carried far more sophisticated cameras, and their close flybys produced the first detailed, high-resolution images and even short, rotating movies of the storm, clearly showing its counterclockwise rotation and revealing, for the first time, the smaller eddies and turbulent structures swirling around its edges, feeding into and peeling away from the storm's main body. It was Voyager's instruments that first detected lightning flashing on the planet's night side, and Voyager's cameras that first allowed scientists to measure the storm's wind speeds with real precision, rather than estimating them from Earth-based telescopic observation alone. The Galileo spacecraft arrived in 1995 and became the first mission to actually orbit Jupiter for an extended period, spending 8 years studying the planet and its moons in far greater detail than any brief flyby ever could. Galileo also released the atmospheric probe we will discuss shortly, sending it directly into Jupiter's clouds, though into a different, calmer region than the Great Red Spot itself, since even mission planners in the 1990s understood that dropping a fragile probe directly into the most violent storm in the solar system would have been an unnecessary risk to a mission with many other scientific goals to achieve. The Cassini spacecraft, en route to Saturn, made a distant flyby of Jupiter in the year 2000 and used the opportunity to conduct an extended, months-long observation campaign of the planet's atmosphere, including detailed tracking of the Great Red Spot's rotation, shape, and interactions with neighboring storms, adding an entire additional data point to the slow historical record of how the storm's size and behavior have changed across the decades. And then, in 2016, Juno arrived, carrying instruments capable of doing something none of its predecessors had ever managed: looking beneath the clouds entirely, rather than simply photographing their surface. Each of these missions, arriving roughly a decade or two apart, across more than 50 years of continuous human exploration, added a new layer to our understanding, the way each new generation of archaeologists might uncover a slightly deeper layer of the same ancient site, using progressively better tools than the generation before. It's worth appreciating, for a moment, just how much this entire body of knowledge represents a genuinely continuous, multi-generational human effort. No single scientist, no single mission, no single spacecraft discovered everything we have discussed tonight. It emerged instead from more than 3.5 centuries of patient, incremental observation, beginning with a single astronomer squinting through an early telescope in the 1660s and continuing uninterrupted through every subsequent generation of scientists and engineers who each added their own small piece to a picture still being completed today. It is worth noting that this multi-generational effort has never belonged exclusively to professional space agencies and their spacecraft. Throughout the 20th and 21st centuries, amateur astronomers around the world, using backyard telescopes far more modest than anything NASA or the European Space Agency has ever launched, have continued a tradition of tracking the Great Red Spot's position, size, and color that stretches back to the earliest organized observation networks of the 1800s. Organizations coordinating amateur observers have collected decades of consistent measurements, tracking the storm's longitude night after night, year after year, building a dataset so long and so consistent that professional planetary scientists regularly incorporate amateur observations directly into their published research, particularly for tracking long-term trends in the storm's drift and size that no single professional mission, with its comparatively brief operational lifetime, could ever capture alone. In a very real sense, some of the clearest evidence we have for the storm's slow multi-decade shrinkage comes not from a spacecraft at all, but from thousands of ordinary people scattered across the world, patiently pointing modest telescopes at the same reddish oval, year after year, adding their own small piece to a scientific record no single generation could have built alone. With that layered history in mind, let's return to the discovery that puzzled Juno's science team so significantly after its arrival. The strange, out-of-place lightning appearing in parts of Jupiter's atmosphere where nothing should have been able to produce it. On Earth, lightning forms through a fairly well-understood process. Water droplets and ice particles collide violently inside towering storm clouds, exchanging electrical charge as they crash into one another until the buildup becomes so extreme that it discharges in a sudden, brilliant flash. This process depends heavily on the presence of water in multiple states, liquid and solid, moving rapidly through a deep turbulent cloud structure. For decades, scientists assumed that Jupiter's lightning, first detected by the Voyager spacecraft in 1979, worked according to roughly the same rules, occurring deep within Jupiter's water-based storm clouds, in a layer of the atmosphere with conditions loosely comparable to a thunderstorm on Earth. Then Juno arrived, and its instruments began detecting lightning in places where it should not have been possible at all. High in Jupiter's atmosphere, in regions far too cold and far too dry for liquid water to exist in any meaningful quantity. This finding puzzled scientists for some time, until a new explanation emerged, one that sounds almost too strange to be real, and yet appears to be exactly what is happening. Deep within Jupiter's clouds, ammonia and water are believed to combine to form a peculiar kind of slushy hailstone, informally nicknamed a mushball, by the researchers who first proposed the idea. These ammonia-water mushballs form when strong updrafts carry water ice crystals upward into ammonia vapor, coating the ice in a slushy ammonia-water mixture that becomes heavy enough to fall rapidly back downward through the atmosphere, carrying electrical charge with it as it descends. This process, entirely different from anything occurring inside Earth's clouds, appears to allow charge to build and discharge at much higher, colder, drier altitudes than would otherwise be possible, producing the strange out-of-place lightning flashes that so puzzled scientists in Juno's earliest data. Juno's instruments have detected these lightning flashes at a considerable rate across Jupiter's atmosphere as a whole, though notably, lightning activity appears to cluster far more heavily near Jupiter's poles than near its equator, a distribution almost the exact opposite of what is found on Earth, where the vast majority of lightning strikes occur in the tropics, closer to the equator, driven by the intense solar heating found there. On Jupiter, the pattern reverses, likely because internal heat rising from deep within the planet plays a proportionally larger role in driving atmospheric convection near the poles than sunlight does, once again reinforcing the central theme of this planet's weather. Internal heat, not solar heating, sits in the driver's seat. If this explanation holds up, and current evidence strongly supports it, it means Jupiter's atmosphere has quietly invented its own version of a fundamental weather phenomenon using an entirely different chemical recipe than the one nature relies on here at home. Water and ice produce lightning on Earth. Water and ammonia, frozen into strange slushy pellets, may be producing lightning on Jupiter, in cloud layers far removed from anything a hurricane on our own planet ever experiences. And this detail matters for our larger story, because it reinforces something we touched on earlier. Jupiter's atmosphere is not simply a scaled-up version of Earth's atmosphere, running the same basic rules at greater size and intensity. In places, it appears to be running genuinely different rules altogether, inventing its own chemical pathways to produce phenomena that, from a distance, look reassuringly familiar, but which turn out, on closer inspection, to be built from entirely unfamiliar ingredients. This raises a quiet, almost unsettling question about the Great Red Spot itself. If lightning on Jupiter can form through a process with no true equivalent on Earth, what other processes might be occurring deep within the Great Red Spot's 300-kilometer roots that have no equivalent anywhere in our own experience? We have measured its winds. We have measured its depth. We do not yet know, with any real confidence, what chemical and electrical processes might be occurring in its deepest, most hidden layers. Layers no spacecraft has yet been built to survive long enough to measure directly. This uncertainty brings us to a companion storm, one considerably younger than the Great Red Spot, but which offers a rare, real-time glimpse into how a storm like this actually begins its life, rather than simply observing one that has already existed for centuries by the time we started paying close attention. In the late 1930s, astronomers began noticing 3 separate white oval storms, forming in roughly the same band of Jupiter's southern hemisphere, south of the Great Red Spot. These 3 white ovals persisted independently for decades, drifting along the same jet stream, occasionally passing close to one another without merging. Then, between 1998 and 2000, in a sequence of events captured by telescopes and later analyzed in detail, these 3 separate storms collided and merged, combining into a single, larger oval storm. At first, this newly merged storm appeared white, much like its 3 predecessors. Then, gradually, over the following years, it began to change color, deepening from white to a pale pink, and eventually to a reddish hue strikingly similar to its much larger, much older neighbor. Astronomers nicknamed it Oval BA, though it quickly picked up a more memorable informal name, Red Spot Jr. Red Spot Jr. gives us something the Great Red Spot itself cannot: a documented birth. We know with reasonable precision when its 3 parent storms first appeared, when they merged, and roughly when its color began to shift. In effect, astronomers have been able to watch, across a single human lifetime, something like a miniature preview of a process that likely happened to the Great Red Spot itself centuries before anyone owned a telescope capable of recording it. This has allowed researchers to test some of their hypotheses about why the Great Red Spot turns red in the first place. If Red Spot Jr. changed color following the same basic physical process, likely involving exposure of certain compounds to increased sunlight, as the storm's internal structure reorganized following the merger, allowing material to be lifted to higher, more sunlit altitudes than before. It offers indirect support for the idea that color in these storms may be linked less to a single, unique chemical fingerprint, and more to the altitude and exposure of whatever chromophore-producing material happens to be present. Regardless of the storm's individual history, Red Spot Junior has also given scientists a rare opportunity to study what happens when two of these giant vortices pass close to one another. On several occasions since its formation, Red Spot Junior has drifted close enough to the Great Red Spot that astronomers worried the two storms might collide directly, an event that had never been observed before between storms of this scale, and whose outcome nobody could confidently predict. Would the smaller storm be torn apart? Absorbed? Would the encounter destabilize the ancient, much larger Great Red Spot itself, ending centuries of continuous existence in a single dramatic collision? In each case so far, the two storms have passed near one another without a direct catastrophic merger, their paths curving around each other under gravitational and atmospheric influence in ways that current models only partially explain. And in one case, Red Spot Junior was observed to be temporarily stretched and distorted by its close encounter, only to slowly recover its rounder shape in the following months, like a smaller boat surviving the wake of a much larger ship passing close by. These near misses matter because they hint at this answer to a question we raised earlier. What would actually happen if a storm the size of the Great Red Spot were to encounter another major storm system directly? Based on what has been observed with Red Spot Junior, so far the answer appears to be that these giant vortices possess considerable structural resilience, capable of surviving close encounters that would likely destroy a smaller, less deeply rooted storm entirely. This resilience appears to be connected to exactly the deep-rooted structure Juno revealed. A storm anchored 300 kilometers or more into the atmosphere is simply much harder to disrupt than a shallow surface disturbance would be, even when a comparably sized neighbor passes uncomfortably close. There is something worth noticing in this relationship between the two storms, something almost narrative in quality, even though nothing about it is designed or intentional. An ancient, 350-year-old storm and a much younger sibling, born from the merger of three smaller storms with living human memory, orbiting the same planet along the same general band of jet stream, occasionally drawing close enough to threaten collision, and each time separating again, both continuing to spin, indifferent to how remarkable their continued survival actually is. Before we widen our view outward, toward Jupiter's influence on the solar system as a whole, there is one more discovery worth pausing on, because it may be the single most visually strange finding to come out of the entire Juno mission, and it changes the way we should think about the Great Red Spot's place within Jupiter's broader family of storms. When Juno's cameras first captured detailed images looking directly down at Jupiter's poles, a vantage point no previous spacecraft had ever achieved, since earlier missions like Voyager and Galileo approached of Jupiter along its equatorial plane. Scientists expected to see something resembling the swirling, chaotic cloud patterns visible everywhere else on the planet. What they found instead looked almost deliberately designed, the way a geometric pattern looks deliberately designed, even when nothing about it actually is. At Jupiter's North Pole, Juno's images revealed 8 massive cyclones arranged in a near-perfect octagon, surrounding a single, similarly sized cyclone sitting directly at the pole itself. At the South Pole, a slightly different arrangement appeared. 5 enormous cyclones surrounding a central polar cyclone, forming a rough pentagon. Each of these individual cyclones is itself a storm system comparable in scale to some of the largest hurricanes ever recorded on Earth. and each has remained remarkably stable in this geometric arrangement across the years. Juno has continued observing them, neither merging together into a single larger polar vortex, nor drifting apart and dispersing into the surrounding atmosphere. This stability puzzled scientists considerably, because basic fluid dynamics would predict that cyclones packed this closely together, all rotating in the same direction, should eventually merge into one another, the way smaller storms are known to merge elsewhere on Jupiter, including in the historical formation of Red Spot Junior, from 3 separate white ovals decades earlier. And yet, at both of Jupiter's poles, this has simply not happened. Across the entire span of time, Juno has been able to observe them. The leading explanation in mind involves a kind of natural repulsion effect between neighboring cyclones, in which each storm generates a ring of counter-rotating air immediately surrounding itself, and this ring effectively pushes against the equivalent ring surrounding its neighbor, keeping the cyclones held apart at a stable distance, much like a group of spinning tops placed close together on a table might repel one another through the cushion of air each one generates around its own edges, preventing them from ever quite touching. If this explanation holds, it means Jupiter's poles are hosting a delicately balanced standoff between more than a dozen enormous storms, each one large enough to be considered a major weather event in its own right, held in a stable geometric pattern, not because anything is actively organizing them, but because the physics of their own rotation happens to naturally produce this kind of self-organizing balance. This discovery matters enormously for how we should think about the Great Red Spot, because it reframes the entire planet's relationship with giant storms. The Great Red Spot is not simply an isolated anomaly, a single unusual feature sitting apart from an otherwise ordinary planet. It is, instead, merely the largest and oldest known member of a much broader family of enormous, long-lived storm systems scattered across Jupiter, from its equatorial bands all the way to its poles. A planet that appears to specialize, in a sense, in generating and sustaining vortices of a size and durability found nowhere else in the solar system. It also raises a question we are unlikely to answer soon. If Jupiter's poles can sustain 8 and 5 massive cyclones respectively, locked in stable geometric arrangements for years without merging, and if the equatorial Great Red Spot has persisted for centuries through its own combination of depth and jet stream positioning, then how many other stable, long-lived vortices might exist across less observed regions of Jupiter's atmosphere, hidden beneath cloud layers or simply not yet imaged in the detail Juno achieved at the poles? The honest answer is that we do not know. And given how relatively recently the polar cyclones were even discovered, Juno's first close polar images were captured in 2016, meaning humanity has known about Jupiter's polar octagon and pentagon for less time than many people have owned their current phone. It seems entirely reasonable to expect that Jupiter still has more of these hidden, stable, long-lived storm structures waiting to be found. It is worth briefly stepping outside Jupiter altogether here, because this pattern of gas giants producing strangely geometric, stubbornly stable atmospheric features is not unique to Jupiter alone, and seeing it repeated elsewhere helps confirm that we are looking at a genuine category of behavior rather than some Jupiter-specific coincidence. Saturn, the solar system's second largest planet, hosts its own famously strange atmospheric feature at its north pole, a persistent, six-sided jet stream pattern, commonly called Saturn's hexagon, first glimpsed faintly by the Voyager spacecraft in the early 1980s and studied in far greater detail by the Cassini spacecraft, which orbited Saturn for 13 years, beginning in 2004. The hexagon is enormous, wide enough that 4 Earths could fit inside its boundary. And unlike Jupiter's polar cyclones, it is not a cluster of separate storms, but a single, continuous jet stream that has organized itself into 6 remarkably straight sides and 6 sharp corners rotating around Saturn's pole with a stability that has now been observed for well over 3 decades. Laboratory experiments here on Earth have managed to recreate hexagonal patterns using rotating tanks of fluid, suggesting that this 6-sided shape may emerge naturally from the interaction between a fast-moving jet stream and the specific rotation rate of the fluid it is moving through, rather than requiring any unusual or exotic explanation. But recreating the pattern in a laboratory tank is one thing. Watching it persist, unchanged in its basic geometry, on an actual planet for over 30 years of continuous observation is another matter entirely, and it reinforces something we have returned to throughout this journey. Gas giants appear to be extraordinarily good at generating atmospheric structures that, once formed, resist the kind of chaotic breakdown we would expect based on our intuitions built entirely from watching weather on a small, rocky, solid-surfaced world between Jupiter's centuries-old Great Red Spot, its geometrically arranged polar cyclones, and Saturn's 3-decade-old hexagonal jet stream. A picture begins to emerge of gas giants as planets that specialize in producing weather with a kind of durability and internal organization that would be almost unthinkable on a world like Earth. It is tempting to imagine that if we could ever build an instrument sensitive enough to closely observe the atmospheres of gas giants orbiting other stars entirely, we might find this same underlying pattern repeating itself again and again across worlds we have never seen and may never see directly. A universal tendency for sufficiently large worlds of hydrogen and helium to organize their turbulent atmospheres into stable, geometric, remarkably long-lived structures, wherever the right combination of rotation speed, internal heat, and atmospheric depth happens to occur. Now let's widen our view considerably, moving away from the storms themselves and toward the planet's broader influence. Because Jupiter's importance to the story of our solar system extends far beyond its own atmosphere into a role that may have quietly shaped the very possibility of a planet like Earth existing peacefully enough for anyone to be here to study it. To understand this, we need to go back once again to the earliest years of the solar system, shortly after Jupiter had finished forming. At this stage, the region beyond Mars was filled with an enormous amount of leftover rocky and icy debris, material that never quite finished assembling into planets, orbiting in what we now call the asteroid belt, and, further out, the region eventually populated by comets. Jupiter's gravity, by far the strongest gravitational influence in the solar system aside from the Sun itself, has been actively sculpting the orbits of this debris for over 4 billion years. One prominent scientific hypothesis, sometimes called the Grand-Tack model, proposes that in the solar system's earliest, most chaotic years, Jupiter itself may have migrated inward toward the Sun, or back outward again, through a complex gravitational interaction with Saturn a kind of cosmic tack of a sailing ship changing direction. As it moved, Jupiter's powerful gravity would have swept through the region where Mars and the asteroid belt exist today, scattering material, preventing a much larger planet from forming in that zone, and possibly explaining why Mars ended up so much smaller than Earth and Venus, despite forming in a broadly similar region of the early solar system. This hypothesis remains actively debated, and not every planetary scientist accepts every detail of the Grand Tack model, but there is broader, less contested agreement on a related point. Jupiter's gravity has, for billions of years, continued to actively shepherd smaller bodies throughout the solar system in ways that are directly observable today. Thousands of asteroids, called Jupiter Trojans, are captured in stable gravitational pockets ahead of and behind Jupiter in its orbit, held in place by the combined gravity of Jupiter and the Sun at two special locations mathematicians call Lagrange points, where the gravitational pull of the Sun and Jupiter balance in such a way that smaller objects can sit essentially motionless relative to Jupiter, drifting along in its orbit like a fixed convoy, accompanying the planet forever. More than 12,000 of these Trojan asteroids have been catalogued so far, and current estimates suggest the true number, including objects too small or too faint for our telescopes to have detected yet, may run into the millions. NASA's Lucy mission, launched in 2021, is currently in the process of visiting several of these Trojan asteroids directly, aiming to study relics that may have remained essentially undisturbed, tucked into Jupiter's gravitational shadow. Since the very earliest years of the solar system's formation, countless comets originating in the distant icy outer reaches of the solar system have had their orbits reshaped by close encounters with Jupiter's gravity. Across the planet's long history, some flung outward into interstellar space entirely, others pulled inward onto orbits that occasionally cross paths with the inner planets, including our own. A distinct family of comets, known as Jupiter family comets, orbit the Sun on relatively short cycles of only a few years to a couple of decades, their paths having been directly shaped and shortened by repeated gravitational encounters with Jupiter over long stretches of time. In a slow, ongoing process of celestial bookkeeping that continues to this day, this is where Jupiter's story connects, quite directly, to a single dramatic event witnessed by astronomers around the world in July of 1994. An event that offered the clearest real-time demonstration humanity has ever witnessed of exactly what Jupiter's gravity is capable of doing to objects that wander too close. A comet discovered the previous year and named Shoemaker-Levy 9 after its discoverers had been captured by Jupiter's gravity years earlier and pulled into a tight orbit around the planet. In July of 1992, the comet passed so close to Jupiter that the planet's immense tidal forces literally tore it apart, fragmenting it into a chain of more than 20 separate pieces, which continued orbiting Jupiter together, strung out like beads on a string. 2 years later, in July of 1994, these fragments collided directly with Jupiter's atmosphere, one after another, over the course of about a week, each impact releasing energy far exceeding anything in recorded human history. Some individual fragments are estimated to have released energy equivalent to hundreds of times the world's entire nuclear arsenal detonated at once. The impact scars left behind in Jupiter's atmosphere were larger than Earth itself, dark bruises spreading across the cloud tops, visible even through modest amateur telescopes, for months afterward. The largest single fragment, designated Fragment G, struck Jupiter on July 18, 1994, and produced a fireball that rose plumes of superheated gas, thousands of kilometers above the cloud tops within minutes, followed by a dark scar in the atmosphere, wide enough to have comfortably swallowed the entire Pacific Ocean. Astronomers watching from Earth and from the Galileo spacecraft, which was still years away from arriving at Jupiter, but already positioned to observe the impacts directly from a distance no Earth-based telescope could match, described the week as one of the most anticipated and closely coordinated observation campaigns in the history of astronomy. With telescopes on every continent, and in space, turned toward Jupiter simultaneously to watch fragment after fragment strike the planet in sequence, each impact confirming that this was not a single event, but a week-long bombardment unfolding in real time. It remains, to this day, the only time in recorded human history that astronomers have directly observed a collision between two solar system bodies of this scale. In real time, with modern instruments actively watching, the event served as a vivid, sobering demonstration of the kind of violence Jupiter's gravity routinely channels. And it also sparked a still ongoing scientific debate about whether Jupiter functions, in some meaningful sense, as a protective shield for the inner solar system, including Earth. The popular version of this idea, sometimes called the Jupiter shield hypothesis, suggests that Jupiter's immense gravity has, over billions of years, captured or deflected large numbers of comets that might otherwise have gone on to strike the inner planets, including Earth, effectively reducing the frequency of catastrophic impacts on our own world, and potentially making the long, relatively stable conditions life needed to evolve more achievable than they otherwise would have been. It is important, in the interest of scientific honesty, to note that this hypothesis has become considerably more contested and nuanced in recent years than it once was. Some more recent computer simulations suggest that while Jupiter does deflect a significant number of long-period comets away from the inner solar system, it may, in certain other cases, actually perturb the orbits of some objects in ways that send them toward the inner planets rather than away from them, meaning Jupiter's overall effect on Earth's impact. History may be considerably more complicated and mixed than the simple, comforting cosmic shield narrative once suggested. The honest scientific position today is less a confident claim that Jupiter has protected Earth in any simple, straightforward sense, and more an acknowledgement that Jupiter's gravity has profoundly shaped the entire structure and history of our solar system, for better and for worse, in ways still being actively studied and debated. What is not contested is the scale of Jupiter's influence itself. No other planet in the solar system has reshaped as much material over as long a span of time as Jupiter has. Whether that influence ultimately worked in Earth's favor, against it, or in some complicated combination of both across billions of years, the great red spot we have spent this entire journey exploring sits atop a planet that has, in a very real sense, been one of the primary architects of the solar system's structure since the very beginning. Jupiter's gravitational dominance does not stop at reshaping distant comets and asteroids. It reaches directly into the planet's own family of moons, and produces, on at least two of them, some of the most dramatic geological consequences found anywhere in the solar system. consequences that connect directly back to the same underlying theme running through this entire journey. What happens when an ordinary process is driven by a force this much larger than anything Earth experiences? Io, the innermost of Jupiter's 4 large moons, is the most volcanically active body known anywhere in the solar system, more active even than Earth itself, despite being a small, rocky moon not much larger than our own. Io's volcanism is not powered by internal radioactive decay the way most of Earth's internal heat is generated. It is powered almost entirely by Jupiter's gravity, through a process called tidal heating. As Io orbits Jupiter, the moon is caught in a delicate gravitational tug-of-war, with Jupiter and 2 of its other large moons, Europa and Ganymede, whose orbital periods lock together in a precise mathematical relationship, forcing Io's orbit to remain slightly elliptical rather than settling into a perfect circle. This slight ellipticity means Io is constantly being squeezed and stretched by Jupiter's powerful gravity as it moves closer to and farther from the planet during each orbit, and this continuous flexing generates enormous amounts of internal friction, heating Io's interior to the point of near-constant volcanic eruption. Io's surface is covered in hundreds of active volcanoes, some producing plumes of material shooting hundreds of kilometers above its surface, repainting its landscape in sulfur compounds so continuously that Io has essentially no impact craters at all, its surface too young and too frequently repaved by fresh eruptions for craters to survive. Slightly farther out, Europa experiences a gentler version of the same tidal flexing, not enough to produce Io's volcanic fury, but enough, most planetary scientists believe, to keep a vast ocean of liquid water flowing beneath Europa's frozen ice shell, kept liquid by exactly the same gravitational squeezing that turns Io's interior into a volcanic furnace. This subsurface ocean is considered one of the most promising locations in the entire solar system to search for conditions that might support life, precisely because it is kept warm and liquid not by sunlight, which barely reaches Europa's icy, distant orbit at all, but by the same relentless gravitational influence responsible for the great red spots opposing jet streams and Jupiter's overwhelming reshaping of the early solar system's debris. There is something worth pausing on here, a kind of quiet, unifying thread running through everything we have discussed tonight. The same spark capable of sustaining a storm, larger than Earth for over 3 centuries. The same planet whose gravity fragmented and consumed a comet in a week of impacts larger than anything in recorded human history, is also, indirectly, responsible for keeping a hidden ocean liquid on a small, ice-covered moon nearly 600 million kilometers from the Sun. An ocean that may, for all we currently know, be quietly harboring life of its own, warmed entirely by the same gravitational muscle that powers everything else remarkable about this planet. Jupiter's influence, in other words, is not confined to violence and destruction alone. The same overwhelming gravity capable of tearing a comet apart may also be the very thing keeping the solar system's best candidate for extraterrestrial life warm enough to exist in the first place. This brings us to a thought worth holding on to as we begin moving toward the end of this journey. The storm churning above Jupiter's clouds and the gravitational forces reshaping comets and asteroids across billions of kilometers are not, in truth, separate stories. Both are expressions of the same underlying fact. Jupiter is, by an enormous margin, the dominant gravitational and atmospheric force in the solar system outside the Sun itself. Its storms are violent because its atmosphere holds an extraordinary amount of energy. Its gravity reshapes distant comets because its mass is more than double that of every other planet combined. Everything remarkable about Jupiter, at every scale, traces back to the same simple fact of its overwhelming size. Let's turn now to the future, to what may eventually happen to the Great Red Spot itself, and to the missions currently working, or soon to work, toward answering some of the questions we have raised throughout this journey, but have not yet been able to fully solve. The Juno mission, which has provided so much of the modern understanding described tonight, continues to orbit Jupiter, its extended mission repeatedly adjusted and renewed by mission planners eager to continue gathering data for as long as the spacecraft's instruments and orbital trajectory allow. Each close pass Juno makes near, Jupiter adds new measurements of the storm's depth, temperature structure, and behavior, slowly refining the picture we have been describing throughout this documentary. Looking further ahead, the European Space Agency's JUICE mission, launched in 2023, is currently making its way toward Jupiter's system, primarily focused on studying 3 of Jupiter's large icy moons, Ganymede, Callisto, and Europa. Worlds believed to harbor vast oceans of liquid water beneath their frozen surfaces, oceans that represent some of the most promising locations in the entire solar system to search for conditions that might support life. NASA's Europa Clipper mission, launched in 2024, is heading toward the same system with a more focused goal, conducting detailed flybys of Europa itself, studying its ice shell and subsurface ocean in unprecedented detail. Neither of these missions is designed primarily to study the Great Red Spot directly, but both will spend years in Jupiter's neighborhood, continuing to observe the planet's atmosphere as a secondary benefit of their broader scientific goals, adding still more data to the slow, patient, decades-long project of understanding this single ancient storm. There has also been serious scientific discussion, though no currently funded mission, about eventually sending an atmospheric probe deeper into Jupiter's clouds than any spacecraft has gone before, potentially descending directly into or near the Great Red Spot itself, measuring its internal structure, chemistry, and dynamics directly, rather than inferring them indirectly from orbit. Such a mission would face extraordinary engineering challenges. Jupiter's atmospheric pressure increases so rapidly with depth that any probe descending into the storm would likely be crushed within a relatively short descent, its instruments transmitting data for perhaps an hour or 2 before the mission's mechanical inevitability arrives. The one previous Jupiter atmospheric probe, released by the Galileo spacecraft in 1995, survived for just under an hour after entering Jupiter's atmosphere in a different, calmer region of the planet, before pressure and heat destroyed it entirely. That single hour, brief as it was, remains one of the most information-dense hours in the entire history of planetary exploration. The Galileo probe transmitted data confirming that Jupiter's winds not only failed to slow down with depth, as some scientists had expected, but actually increased in speed the deeper the probe descended, suggesting that Jupiter's storms may be powered less by the sunlight and shallow atmospheric heating that drives Earth's weather, and more by the deep internal heat rising from below, exactly the kind of evidence that would later support the broader picture Juno confirmed decades afterward. The probe also happened to descend into an unusually dry, clear patch of atmosphere nicknamed a hot spot, which contained far less water vapor than scientists had expected to find, a discovery that puzzled researchers for years afterward and remains only partially resolved today, since it is still unclear whether the probe simply had the misfortune of entering an unusually atypical region or whether Jupiter's atmosphere as a whole contains less water than earlier models predicted. A probe descending directly into the Great Red Spot would face conditions likely more extreme still, given the storm's far higher wind speeds and turbulence compared to the calmer region. Galileo's probe happened to enter, and no space agency has yet committed the resources such a mission would require. For now, our knowledge of the storm's true depths remains built entirely from remote sensing, careful inference, and the single, tantalizingly brief hour of direct atmospheric data Galileo's probe managed to gather from a different part of the planet entirely. This is worth sitting with for a moment, because it reveals something important about the limits of what we currently know, and what we may never fully know about this storm, everything we have described tonight. The depth, the wind speeds, the possible chemistry behind its color, its uncertain future, has been pieced together entirely from a distance through remote sensing, orbital measurement, and careful physical modeling. No human instrument has ever survived long enough or been built robust enough to descend directly into the Great Red Spot and report back what it actually finds at its deepest layers. Everything we know is inference, however well supported by data. The storm's true interior remains, in the most literal sense, beyond our direct reach. This should not diminish anything we have discussed tonight. If anything, it should deepen the sense of wonder surrounding it. We have built an extraordinarily detailed picture of a storm we have never directly touched, using nothing but light, radio waves, gravity measurements, and careful reasoning from a spacecraft that has never physically entered the storm itself. That is, in its own way, one of the most remarkable achievements of modern planetary science. Understanding, in genuine and substantial detail, something we may never be able to physically access at all. Before we return to the question that opened this journey, there is one more comparison worth making, because it recalibrates our sense of where Jupiter's storm actually sits on the true spectrum of what atmospheric physics allows across the universe as a whole, rather than simply within our own solar system. In recent years, astronomers have managed to measure wind speeds directly on a small number of gas giants, orbiting other stars entirely, using extremely precise spectroscopic techniques capable of detecting the faint Doppler shifts caused by fast-moving atmospheric gas, even on planets too distant and too faint to photograph directly. One planet in particular, an exoplanet named HD 29733b, orbiting a star roughly 64 light-years from Earth, has become something of an unlikely celebrity in this field of research. Measurements of its atmosphere suggest wind speeds along its equator may reach roughly 2 kilometers per second, nearly 7,000 kilometers per hour, more than 15 times faster than the winds measured at the edge of Jupiter's Great Red Spot, and comfortably faster than a rifle bullet leaving the barrel, because HD A9733b orbits so close to its star that a full year on the planet lasts just over 2 Earth days. Its atmosphere is heated to temperatures at which astronomers believe silicate particles, essentially the same basic material that makes up window glass and sand here on Earth, condense directly out of the atmosphere at high altitude, and some models suggest these ferocious winds may drive that condensed material sideways in something resembling horizontal rain. Made of glass, moving at speeds no storm on Jupiter has ever approached. We mention this not simply because it makes for a striking image, though it certainly does, but because it offers real perspective on everything we have described tonight. For this entire journey, we have treated the Great Red Spot's winds, 430 kilometers per hour, as almost incomprehensibly fast compared to anything Earth produces. And they are. And yet, somewhere among the stars, an entirely different gas giant, close enough to its star to be measured directly from Earth using modern instruments, appears to host winds moving more than 15 times faster still. The Great Red Spot, for all its centuries of persistence and all its violence by Earth's standards, may actually be a relatively gentle example of what gas giant weather is capable of becoming once a planet is placed close enough to a star to be baked by heat, far more intense than anything Jupiter, sitting comfortably distant from our own sun, will ever need to endure. Before we return to the question we opened this journey with, it's worth sitting directly with a possibility we have circled around several times tonight without confronting head-on. What would it actually look like, mechanically, if the Great Red Spot finally did come to an end, based on everything we have discussed? Neptune's great dark spot vanishing within 5 years, the storm's own slow multi-decade contraction, its increasingly circular shape. Most planetary scientists who study the question closely tend to favor one of two broad outcomes, while remaining honestly uncertain about which is more likely or how soon either might occur. The first possibility is a relatively swift dissolution, similar in character to what happened on Neptune. In this scenario, the storm would continue shrinking and rounding for some further period, gradually losing the structural tension that currently holds its winds together until at some point, potentially within a matter of years, once the process reaches a critical threshold, its organized rotation would break down entirely, its material dispersing outward into the surrounding jet streams, the way a whirlpool disperses once the object holding it in place is removed. Under this scenario, the transition from clearly visible giant storm to no storm at all could plausibly happen within a single human decade, a strikingly fast ending for a phenomenon that took centuries to observe. The second possibility is closer to stabilization than disappearance. Under this view, the storm's contraction is not a terminal decline at all, but rather a settling process in which the Great Red Spot is gradually finding a new, smaller, but genuinely stable equilibrium size, one at which its remaining energy, drawn from Jupiter's internal heat and the surrounding jet streams, is sufficient to sustain it indefinitely, simply at reduced dimensions. Compared to the 19th century storm, first measured by early astronomers. Under this scenario, the Great Red Spot we see today, or some further slightly contracted version of it, could plausibly continue existing for additional centuries, essentially unchanged in its basic persistence, just smaller than the version that first captured astronomers' attention 150 years ago. There is also a third, more unsettling possibility worth acknowledging honestly, precisely because it fits the pattern of scientific humility we have tried to maintain throughout this entire journey. It is entirely possible that neither outcome is currently favored, and that our data, spanning barely a century and a half of careful measurement against a storm potentially several centuries old, is simply too limited to make a confident prediction. Either way, we may be watching a genuine ending unfold in slow motion. We may be watching an ordinary fluctuation within a much longer cycle we do not yet have enough historical perspective to fully map. Both possibilities remain live scientific hypotheses today, and the honest, current answer is that nobody studying this storm closely enough to have a real opinion is willing to state with confidence which one is correct. What we can say with more confidence is this: whichever outcome eventually occurs, it will happen entirely according to Jupiter's own internal timetable, driven by forces: internal heat, rotational speed, jet stream dynamics, that operate on scales of energy and time utterly indifferent to human observation. If the storm does eventually end, it will not end because we watched it closely enough to cause it, or because our spacecraft disturbed it in some way. It will end, if it ends at all, for the same reason it has persisted for centuries: because of forces working silently within Jupiter's atmosphere, exactly as they have been working since long before any telescope was ever pointed toward this planet. Let's return one final time to the question we opened this entire journey with. Why is Jupiter's great red spot more terrifying than any storm on Earth? By now, the answer should feel different than it did at the beginning. It is not simply about size. Though the size is real and almost incomprehensible, it is not simply about wind speed. Though the wind speeds genuinely exceed anything Earth has ever produced, it is something quieter and, in some ways, more unsettling than either of those facts alone. It is the absence of an ending. Every storm we have ever personally feared on Earth carries, built into its very structure, the seeds of its own eventual defeat. Coastlines wait to weaken it. Mountains wait to shred it. Cool, dry land waits to starve it of the moisture keeping it alive. We fear hurricanes, but we also understand, somewhere in the back of our minds, that they cannot last. They are, by the basic physical structure of our world, temporary. The Great Red Spot carries no such built-in ending. It exists on a world with no coastline, no mountain range, no solid ground anywhere to eventually collide with and dissipate against. Its energy comes from sources: Jupiter's ancient internal heat, the planet's rapid rotation, the opposing jet streams trapping it in place, that are not going anywhere on any timescale that matters to a human life, or even to human civilization as a whole. Whatever eventually happens to this storm, whether it continues shrinking slowly over the coming decades, stabilizes into a smaller but enduring form, or eventually follows the path of Neptune's vanished great dark spot and dissolves back into the surrounding atmosphere, within a surprisingly short span of time, its fate will be decided entirely by forces internal to Jupiter itself, on a timescale utterly indifferent to anything happening on the small, rocky, storm-limited planet where we happen to live. That is the true source of the unease sitting underneath everything we've discussed tonight. Not that the storm is big, not that the storm is fast, but that the storm exists inside a version of nature where the rules protecting us from our own weather simply do not apply. A demonstration, close enough to study directly, of what our own planet's atmosphere might eventually resemble if it, too, lost the coastlines and mountains and solid ground currently keeping every one of our storms in check. And perhaps that is the quiet gift hidden inside a story like this one. Not fear for its own sake, but a sharper appreciation for the very things about Earth we rarely think to be grateful for. The coastlines that limit our hurricanes, the mountains that break apart our storms, the solid ground beneath every one of us, patiently absorbing and dissipating energy that, on a world like Jupiter, would simply continue circulating, unchecked, for centuries. We began this journey looking outward, toward a storm larger than our entire planet, spinning above clouds none of us will ever personally see with our own eyes. We end it, as these journeys so often do, looking back toward home with a slightly clearer sense of just how carefully balanced our own quiet corner of the solar system actually is. A world with coastlines and mountains and solid ground, and storms that, however frightening they may feel in the moment, always, eventually, come to an end. There is a particular kind of perspective that only seems to arrive after spending real time with a subject like this one, rather than simply skimming a headline about the biggest storm in the solar system and moving on. It is the perspective that comes from sitting, for a while, with genuine scale. Not scale as a number to be memorized, but scale as something closer to a feeling, settling in slowly the longer you allow yourself to think about it. Consider for a moment everything this single storm has quietly outlasted. Every war fought across the past 2 centuries, every empire that rose and eventually dissolved, every technology invented, refined, and rendered obsolete by something newer, every person who has ever looked up at Jupiter through a telescope and wondered about it, from the earliest observers in the 1600s to whoever might glance up at Jupiter tonight from a backyard telescope of their own. All of that history, all of that human striving and building and forgetting, unfolded entirely within the lifetime of a single storm that, as far as we can tell, has no particular reason to stop anytime soon. This is not a comfortable thought in the way that wonder is sometimes comfortable. It carries a little of what earlier we called cosmic humility, the quiet, clarifying realization that the things we build our lives around, the time scales that feel enormous and significant to us personally, are almost unnoticeably brief when measured against even a single weather event on a neighboring planet. And yet, there is something genuinely steadying in that same realization, rather than only something unsettling. If a storm can spin unbothered for centuries, entirely indifferent to the news cycles and anxieties of whichever decade happens to be passing beneath it, then perhaps there is a kind of freedom available in remembering just how small our most pressing daily concerns actually are. Set against a backdrop this vast, Jupiter itself offers no answers about how to feel about any of this. It does not know it is being watched. It does not know its storm has a name, or that generations of astronomers have devoted entire careers to measuring its wind speeds and guessing at the chemistry behind its color. It simply continues, exactly as it has since long before any human eye first noticed it, exactly as it likely will long after the last human eye capable of noticing it has closed for good. And perhaps that indifference is, itself, the deepest source of wonder in this entire story. We have spent this evening building an elaborate, careful, scientifically grounded picture of a storm that has absolutely no awareness that any of this effort is happening. Every measurement, every hypothesis, every spacecraft sent across hundreds of millions of kilometers to study it more closely has been entirely one-directional, an act of attention flowing outward from a small, curious species on a small storm-limited planet toward an ancient, oblivious, magnificent weather system that will never know it was noticed at all. That, in the end, may be the truest answer to the question we asked at the very beginning of this journey. Why is the Great Red Spot more terrifying than any storm on Earth? Perhaps because it is the closest thing we have ever found to proof that the universe does not require our attention in order to keep doing exactly what it has always done. It does not need us to marvel at it. It does not need us to measure it, name it, or send spacecraft to study it. It was already ancient and enormous and violent long before we existed to notice. And it will, in all likelihood, remain exactly that long after we no longer can. And yet here we are noticing anyway. Building spacecraft, launching them across the solar system, pointing instruments at clouds we will never touch, trying patiently and persistently across generations to understand something that owes us no explanation whatsoever. There is something worth holding on to in that fact alone, not the storm's indifference to us, but our own refusal to be equally indifferent to it. There is a quiet kind of invitation hidden inside a story like this one, if you are willing to notice it. Tonight, we followed a single storm from the surface of its clouds down through 300 kilometers of hidden structure, out through its family of sibling storms scattered across Jupiter's poles, and further still, into the gravitational forces that shaped comets, asteroids, and possibly even the safe formation of the very planet we call home. And even after everything we have covered, we have still only traced a fraction of the questions this one storm continues to raise. We do not know, with confidence, exactly which molecule paints it red. We do not know, with confidence, whether it is quietly dying or simply settling into a new, smaller permanence. We do not know what its deepest layers, far beyond anything a spacecraft has survived long enough to measure, actually look like, or what strange chemistry might be unfolding there, entirely unseen. Those unanswered questions are not a disappointment. They are, in their own way, the most honest ending a story like this one can have. The universe rarely finishes its explanations conveniently in time for us to close the book feeling complete. It simply continues being larger, older, and stranger than whatever we currently understand of it, offering just enough certainty to satisfy curiosity for one evening, while quietly reserving enough mystery to make the next evening, and the next telescope, and the next spacecraft worth returning for. Jupiter's storm does not know this about itself. It has no coastline waiting to receive it, no mountain waiting to break it apart, no ending written into the physical structure of the world containing it. It has simply been turning for longer than anyone currently alive has existed, indifferent to the small, temporary, storm-limited world, watching it from 100 million kilometers away. It is very likely still turning right now, as this documentary comes to its close. It was turning long before any of us arrived to notice it. In all probability, it will still be turning long after we are gone, waiting patiently and without any awareness of waiting at all, for whichever future astronomer, on whichever future evening, next happens to point a telescope toward that quiet, ancient, restless red eye in the clouds of Jupiter, and wonder, as we have tonight, exactly how something like this came to exist, and exactly how much longer it might continue.